Hi guys, welcome to the solution to the 11th riddle in the Flare On challenge. This time it's pretty straightforward what we have to do. It's a command line application. If we start it, it just displays the text nope, and we have to find out what to do to get the flag. Detected Easy says that this appears to be just some C++ application. It's only 120K and it doesn't appear to be packed or encrypted or something. So how bad can it be? Pretty bad, as I had to find out the hard way. Apart from being littered with crap logic all over the place, there are multiple dispatch loops like this one here, where it just iterates over a jump table and then calls the methods inside. And what this actually does is it prevents a static analyzer like IDA Pro or Ghidra from sweeping through all available functions for disassembly. The application will emit the correct flag if you specify the right command line arguments. And what makes it really hard to get a solution to this one is that the logic to validate the command line arguments is scattered to many different places. Before the routine you see here, it has validated that there are two arguments passed over to the executable. I call them code 1 and code 2 in the following. And code 1 has to have a length in between 5 and 32 characters. And code 2 has to be exactly 32 characters. Now this here is the core of the application. Though at first sight it looks very similar to the dispatch loops we saw before, it's conceptually different. What happens here is that it's running a virtual machine inside this code. You see that it's iterating over a memory area, then reading EAX from the current pointer, and then based on EAX it makes a jump. And it takes what comes after EAX as the arguments for this jump. So what happens here is we have some virtual opcodes implemented, and these do some operations inside this virtual machine. The idea to implement a virtual machine to prevent disassembly is not new. It's used in several commercial protections. Somehow you hear about AAA game titles being significantly slower because of using this kind of protection. But in my opinion, this doesn't really make sense. Before analyzing the virtual machine itself, let's have a look on what happens afterwards. There are two final checks happening before the flag is displayed to the user. The first one takes two registers from the virtual machine and checks if they are equal. The second goes ahead and checks if code 1 entered equals Flare 2019. So we are searching for a 32 character code that contains printable characters. The flag to be displayed is calculated by applying an XOR to code 2 and a register in the virtual machine, and finally appending at flareon.com. So next I step through the virtual machine, searching for the commands that are actually available, and I started a C# project that implements this virtual machine. Here you can see the definition of the commands, where the key in the dictionary is the bytecode being used for the command, and that class is the implementation of the command. Three of these commands are somewhat special. Clear goes ahead and sets all registers in the virtual machine to 0. Load loads a register with a given value, and exit, which you do not see in this list, goes ahead and exits the virtual machine. The machine has 32 registers of 32 bytes each, that's 256 bits. To get the flag, register 2 and register 14 have to be equal. Apart from the special opcodes I discussed before, all other opcodes are just calculation operations that take two registers as an input and emit to one target register. And what makes this challenge somehow complicated is that the implementation of these opcodes are SIMD instructions. That's newer instructions on the x64 processors, where you manipulate multiple values in one step. And the problem is that the documentation on this is really scant. So here you see the virtual machine running. Register 0 is code 1, register 1 is code 2, and you see that the operations work on the other registers, and in the end you will arrive at the state where register 2 and register 1-4 are compared to each other. Before the values of the registers, you optionally see 1 and 2. These are just markers when data from code 1 or code 2 are somehow influencing the value of a register. So I can see when the codes that are appended to the command line are propagated into a register. At the point where I implemented this, I did not know that code 1 has to be Flare 2019 anyway. In case I knew, I would have left it out. Fiddling around with different values of code 2, I found out that 4 characters of code 2 always end up in 3 bytes from register 2, and that register 1-4, though it is marked as being dependent on code 2, is always a constant. This means that I can break down code 2 into 8 equal parts of 4 characters and brute force them individually. Brute forcing took about an hour, and this gave me code 2, and finally the program displayed me the flag for the challenge.